What's up, AP Calc students? This is 5.5.2 homework, 168 through 172. I know I'm kind of dumping a lot on the weekend here. We're moving forward quite a bit. Hopefully this video helps you get through this. This is a pretty short one anyway. We skipped a lot of stuff, so kind of condensing two homework assignments down into one with the shorter one last time and this one also. 168, we got a bunch of limits here. This is going to give us a chance to practice both our understanding of limits and L'Hopital's rule. So for question A, each one of these is kind of unique and different, like its own little puzzle. So let's focus on question A for a moment here. First thing you want to do is plug in the number. Take the limit you're approaching and plug it in. If you plug in 1 here, you are going to get a 1 minus 1 on top and a 1 squared plus 1 on bottom. And here, the thing here is that the bottom is just 2, so there's nothing really to worry about in this particular limit because you end up getting 0 over 2, which is just 0. So that's it. The answer to this question is 0. Limit questions don't have to be complicated, especially if you just plug in the number and you don't get anything that causes an issue. So in this case, the answer is just 0. And there's nothing really more to say about it because plugging in 1 doesn't do anything. With B, though, if you start plugging in 2 into this equation, you'll realize right away, if you plug in 2 to the third power and 2 squared, that's going to give you 8 minus 8 and 4 minus 4, which is 0 over 0, which gives us the indeterminate form that we will talk about in class today. And the indeterminate form is what says that now, we have to use some sort of procedure here. Now, because we have this, there's actually a couple different ways to do this limit. Limit as x approaches 2 of x to the third minus 8 over x squared minus 4. Now, if you're an astute algebra student, you might already know that this is a difference of squares and a difference of cubes. The bottom can be easily factored into x minus 2 and x plus 2, for example, and the top can be less easily factored into x minus 2, x squared plus 2x plus 4, like that. Now, you could do it this way. I do not recommend that you use this strategy because it really relies on you having memorized the difference of cubes, which is not a thing that I think a lot of students memorize, including myself. I have to Google it every single time. So at this stage, you could cancel out the x minus 2's, and now you can plug in 2. And plugging in 2 will give you 12 over 4, which is 3. And that is the correct answer. However, once you've determined that you have the indeterminate form of 0 over 0, what we could do instead is use L'Hopital's rule, which is the strategy that I do recommend because L'Hopital's rule works for a lot of cases, not just this one special case. So if you're going to memorize something, memorize L'Hopital's rule, which is easy to do. All we got to do here is take the derivative of the top and the bottom. This would give us 3x squared over 2x. That's it. Take the derivative of the top and the bottom. The constants of 8 and 4 cancel, or they go away, and x to the third becomes 3x squared, and x squared becomes 2x. Now, when you plug in 2, you get 3 times 2 squared over 2 times 2, and that, again, is 12 over 4, or just 3. So you can do this one by factoring or by using L'Hopital's rule, but either way, it's not a very difficult limit. But I recommend L'Hopital's rule as the strategy that you start using for most limit problems. For question D, we have a limit as x approaches infinity. Now, if you think about this for a moment, there is no current way to evaluate this. But if you plug in infinity, which is a weird thing to plug in, all we have to do is show that we get an indeterminate form. And if you plug in infinity to both these functions, you will get infinity on top and infinity on bottom. They both go to positive infinity, and that is also an indeterminate form, which means that L'Hopital's rule does apply. So we're going to use L'Hopital's rule again. I'm going to move this off to the side and do the work over here. This is for question C. We're looking at the limit as x approaches infinity of the square root of x over 3x plus 4. And again, L'Hopital's rule says that since this limit is an indeterminate form, this will equal the limit as x approaches infinity of its derivative. So how about 1 over 2 roots of x, which is the derivative of the square root of x, divided by 3. This limit does exist because if you plug in infinity for x, look at what happens. If you plug infinity in for x, actually there's only one x to plug it into right there. Now that does go to infinity, but it's also the bottom of a fraction. So this becomes kind of 1 over infinity divided by 3, which is the same kind of idea as 0 over 3, which is why it's 0, like that. And the limit is 0 in this question, and that's it. L'Hopital's rule makes limits much, much easier, especially when they're fractions, because that's what 90% of the problems are in limit problems. Question D, again, we got a limit as x approaches 0 of the sine squared of x over the sine of x squared. If we plug in 0 for these things, we do get 0 over 0. Sine squared of 0 over the sine of 0 squared. Both of these end up calculating the sine of 0, which is 0. So you do get 0 over 0. And so once again, you've got an indeterminate form going on. So you can use L'Hopital's rule. Now, L'Hopital's rule in this case will be a little more complicated because these derivatives are going to require the chain rule, but that gives us a good chance to practice chain rule. Again, we're looking at the limit as x approaches 0 of the sine squared of x over the sine of 2x, or sorry, x squared. Now, both of these derivatives are going to require the chain rule, and that, again, L'Hopital's rule will say that this is equal to the limit as x approaches 0 of the derivatives of the top and the bottom of this fraction. Both of these fractions actually involve, both these functions on the top and the bottom have the exact same two functions. One of them is the sine of x, and the other one is x squared. But they're in different orders here. On the top, you have the sine squared of x, which is the sine of x being squared. So the first thing we have to do is evaluate the squared with the power rule. It will be 2 times the sine of x to the first power, and we're going to multiply that times the cosine of x, which is the derivative of the sine. So we're going to chain rule out the derivative of sine. On the bottom of the fraction, however, we are going to get, vibe with me for a minute here while I drink my coffee. This time, we need to take the derivative of the outside chunk, which is, this time the outside chunk is the sine. So that would be the cosine of x squared times the sine of x. Sine times 2x, which is the derivative of the inside part. Now, unfortunately for us, you'll notice if you're looking at this, if you plug 0 in for x again in this problem, you end up getting a 0 over a 0, because the sine of x becomes 0 and 2x is also 0. And unfortunately, that's also not going to work for us. At this stage, I'm looking at this problem and I'm looking at the answer. It looks like the answer is going to be at 1, and now I'm trying to think about how I'm going to get this. So I'm going to plan ahead. This also goes to 0 over 0. So I think trying to use L'Hopital's rule again is what my instinct says. So I'm going to try it. Now this is going to be equally complicated because we have a quotient rule, or sorry, a product rule going on both the top and the bottom. So just kind of vibe with me. I'm going to work through it kind of slow as best I can. I'm taking my time with these videos. If you've noticed the videos getting longer, I'm taking more time to explain things in them because I know you guys are using them later on as an instructional resource, which is a good thing. So for the top of this fraction, let's treat this chunk as the first thing and this chunk as the second thing. So it would be the original first, 2 sine of x, times the derivative of cosine of x, which is the sine of x, or sorry, negative sine of x, plus the original first thing, the cosine of x, times the derivative of 2 sine of x, which would be 2 cosine of x. So just running through a product rule there. Again, it's the original first times derivative of second plus the original second times derivative of first. We could clean that up, but we're going to plug 0 in for everything, so it's not really worth cleaning up right now. On the bottom of the same kind of thing, we're going to treat the cosine of x squared as the first thing and the 2x as the second thing. Again, that the original first thing will be the cosine of x squared times the derivative of the second thing times 2 plus the original second thing, 2x, times the derivative of the first thing, which is also going to require another chain rule. This will be the negative sine of x squared times another 2x, because we need another chain rule to pop out. Like that. Now, don't panic too much on this one, because we're going to plug in 0 for x. And really, if you think about this, if you plug a 0 into the sine of x, or the negative sine of x for that matter, and if you plug a 0 into, again, the sine of x squared, or 2x, these whole chunks of the problem are just going to be 0. All of them. However, the other parts of the problem will not be 0. Cosine of 0 is equal to 1. So this ends up, if you look at what's going on here, this is going to shake out to be, this is 1 times 2. Right there. And right there, that is also 1 times 2. So we end up getting 2 over 2. 2 plus 0 over 2 plus 0, which is actually 1, which is why the final limit is actually equal to 1. That's a good example of a limit that requires 2 examples of L'Hopital's rule. L'Hopital's rule didn't work the first time. It still gave us an indeterminate form right there. But if we did it again, we got something that did give us a final answer. So that's a good example of a double L'Hopital's rule. Let's shift gears from limits and go into problem 169 with kind of a maximum and minimum question. This one's a little interesting because it leaves things nice and flexible. The formula h of x equals x minus 2 times ax minus 1 squared. It's defining a family of functions, each corresponding to a different value of a parameter a. Determine the values of x for which this family of functions has a relative maximum or a minimum, and your answers will be in terms of a. So, don't let this block of text intimidate you too much. We're looking for relative maximums and minimums. Those are going to happen when f prime of x, or I guess in this case, h prime of x. We're looking for when h prime of x will change sign. So let's start by taking the derivative, h prime of x, and setting it equal to 0. That'll help us at least identify some critical values where that could potentially happen. So for this derivative, it's debatable whether you want to expand it out or use the product rule. I think I'm going to expand it out, though. Let's start by doing a little bit of algebraic work with our original function, x minus 2 times ax minus 1 squared. This is going to be x minus 2 times, if we expand this out, this will be a squared x squared minus 2ax plus 1. And if we multiply this times, if we distribute and do a lot of, again, heavy algebra here, this would be a squared x to the third minus 2ax squared plus x. That would be for the x pieces. And then for the 2 pieces, we would have minus 2a squared x squared plus 4ax minus 2, like that. And I don't think any of this combines together to make like terms. Very cool. Again, I'm starting to think whether this would be easier to do with the chain rule, or the product rule, but I don't, the product rule would require a chain rule anyway, so I don't know if it would be any faster. Anyway, actually, this is going to be pretty simple because what we're going to do next is we're going to take the derivative of this. We're going to do h prime of x. And again, h prime of x means that x is the operating variable. A is just a constant, so we don't have to worry about its derivative. This is going to give us 3 times x squared, a squared in that first chunk, minus 4ax for the next one, plus 1. Minus 4a squared x in that chunk, plus 4a, and then the 2 will just go away, minus 2. Let's see. Now the challenge is going to be, how can I separate this out and think about, how can we find places when this is going to equal 0? We could try to make it into a quadratic. I'm going to try a thing really quick, and then I'm going to try a different strategy for this problem, I think. If I combine together the parts where x is being squared, well, we've got 3a squared times x squared minus 4a minus 4a squared times x. Oof, that's not fun. plus 4a plus 1. I'm trying to think about this like a quadratic equation, I guess. Nah, you know what? At this point, I'm going to say I ran into a brick wall right here. I'm going to draw a little brick wall. Ran into one here. Let's try a different strategy. I think maybe the more I think about it, maybe that chain rule, product rule thing might be a better plan. Let's try that. H of x is equal to x minus 2 times ax minus 1 squared. Let's try to do this with the product rule instead of expanding it all the way out. H prime of x here, well, let's see. It would be the original first thing, x minus 2, times the derivative of the second thing. And that would be tougher to get, because that's going to require the chain rule, but still not too terrible. Times, it would be 2 times ax minus 1 times the derivative of the inside part, which would just be a. Yeah. That would be the first chunk of the product rule, so plus the original second thing, ax minus 1 squared, times the derivative of x minus 2, which is just 1. So there's that. So if we clean this up a little bit, what we'll have is we'll have 2a times x minus 2 times ax minus 1 plus ax minus 1 squared, like that. And again, the challenge here is to figure out when this is going to equal 0. What would cause this to be 0? Well, I know one way we can get it. It would be to, one way we can get it is by factoring out an ax minus 1, which we have in both of these terms right there. So we can factor an ax minus 1 out. We can turn this into a multiplication problem. That would turn it into 2a times x minus 2 plus ax minus 1, like that. Factoring out, pulling it 1 ax minus 1 out of both those terms. Now it's a multiplication problem that equals 0, which is always handy because we can think about when each part equals 0. Because if ax minus 1 equals 0, then the whole thing is 0, and that's going to happen when x is equal to 1 over a, and that is one of the zeros that I see there. The other one would be this guy here, this whole chunk. What would happen if that equals 0? We'd have 2a times x minus 2 plus ax minus 1 equals 0. Let's solve this for x. It actually won't be too hard to do, because if we distribute this, we get 2ax minus 4a plus ax minus 1 equals 0. And we can actually isolate the x really easily here, because we can combine the like terms together. This is 3ax minus 4a minus 1. And remember, we don't really care about what a is. We just got to get x by itself. So let's get everything that's not x out of there. Let's move that 4a and that 1 to the other side. We'll add them both to both sides, plus 4a plus 1. And then we'll divide everything by 3a. And that will give us x is equal to 4a plus 1 over 3a. And that is the other answer. Yeah. Now, I don't really know which one's going to be minimum, which one's going to be maximum, but the answer guide I'm looking at on the other monitor just says that those are the potential places that it could be. And again, we don't know what a is. A is a general number that's left alone, so that is the process right there. So it looks like in the end of the day, the best thing to do was to just use the product rule and the chain rule. I tried to make things easier and then ran into a way worse problem than I wanted to do. So that is that's a pretty tough problem. I'm not gonna lie. That if you're head scratching a little bit right now or feeling defeated, it would be okay. It'd be okay. Just look at it for a minute, let it try to sink in. If the problem beats you up a little bit today, you get it again the next day. It's okay. Let's move on to the next one. Let's try 170, where we got some antiderivative questions, and a couple of these are just knowledge antiderivatives. The first two, for example, or sorry, A and C, at least. These are just knowledge antiderivatives. Do you know what the antiderivative of sine is? In this case, the capital F of x, the thing whose derivative is just a regular old sine, that would be a negative cosine. Plus c. Don't forget the plus c on there too. Because the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. We'll jump down and do c right away also, because this is another one. Do you just recognize that? Which trig function has a derivative of the secant squared, and that is the tangent of x plus c. That's going to be the warm-up we're going to do today in class 2. That's an actual AP question. That's cool. Now for questions B and D, we're going to need to get a little more involved than that, because we're going to need to think about things a little clearly. For b, let's think about this as 2 times x plus 3 to the negative third power. First of all, you might be concerned about chain rule, which would be a good thing to worry about, but don't panic too much because the derivative of x plus 3 is just 1. So the chain rule doesn't actually need to worry us here. We are going to need to write an antiderivative for this. So the capital F of x in this problem, we're going to take this up a degree. We need x plus 3 to be to the negative second power. And when we bring that negative 2 down, we need to multiply it by something to make it positive 2 right there. So let's just make it negative x plus 3 to the negative second power. That way, when we take the derivative, the negative 2 will come down, multiply with the negative, and make positive 2. And then it will drop down a degree and make negative 3. That will work. Plus c. Don't forget the plus c. Cool. For question D, again, we got to think about the reverse power rule. I think it's usually a good idea to think about this as 3x to the negative third power plus 2x to the negative fourth power, because that helps to think about your antiderivatives. Again, the antiderivative of 3x to the negative third, well, let's start with x to the negative second, because we have to drop it down a degree. And then we need to think, okay, negative 2 times what will give us this negative, or that positive 3 there? I think it's going to have to be negative 3 over 2. Like that. That way the negative 2 comes down and multiplies and cancels out with the 2 underneath and cancels out the negative and leaves it with just 3. You got to have that. That'll do it. The other one is, let's start with x to the negative third power. Because again, when we take the derivative, we need to drop it down to the negative 4 right there. And again, the question becomes, okay, negative 3 times what is positive 2? Well, a really good way to do this is to just put a 3 down here so that cancels out, and just put your negative 2 right there. Put a plus in between them like that. That will do the trick. Negative 3 comes down, cancels out the 3, cancels out the negative, and leaves the 2. Don't forget plus c either. Those are kind of tricky, but just take your time with them a little bit. You'll get the hang of it. As you build fluency, as you build fluency, you can go faster. Don't worry about speed right now. With 171, we're going to use the calculator for most of this question, so let's just go to the calculator. We'll leave some space to write a few things. This is a good thing to get used to being able to do. So we're going to calculate the area of the region bounded by the curves with those two polynomials there. So let's go open up the old calculator cam. Let's get calculator cam active, actually. Hey, wake up. Here you are. Okay, I'm going to switch out, make sure my calculator's in function mode, first of all, not polar mode. So let's talk about x to the third power minus 8x squared plus 20x. We'll start there. And let's talk about negative x squared plus 8x. And let's go ahead and just graph these on a standard Zoom 6 window so we can see what's going on. Let's try to figure out where they intersect. That's kind of the first challenge here. Where do these two things cross? There is the first thing, and there is the second thing. I'm going to need to change the window a little bit because I don't see that second intersection. I suspect it's probably up here somewhere. So let's, since we don't need this negative space down here, let's change the window from like -1 to, we'll leave -1 to 10. That's fine. But for y, let's go from -1 maybe to 30 or so with a scale of 5. That'll help us see what's going on there. There is the first graph in all of its glory, and here's the second graph right there. Now that's interesting because when we say calculate the area of the region bounded by, if you're looking carefully, we actually have two regions to worry about. We have two different spaces here. These two graphs cross twice, once there and once there. This looks like it's x equals 3 and x equals 4, but I don't know. These are probably going to be weird decimals, so let's do some writing. I do think it's true that if we plug 0 into either one of those functions that we get 0. So I know they do cross at the point 0, 0 to begin with. Now just to help color code things in our head, this is the blue function, the cubic function, and this is the red function, the quadratic function. So the first integral that we're going to need to calculate is the integral from 0 to something. I don't really know what that top bound is yet. Of, in parentheses, x to the third minus 8x squared plus 20x, that would be the top function, for at least that span of the integral, minus negative x squared plus 8x. That would be the bottom function. And this is all, of course, times dx, because it's an area model like that. We need to figure out what that intersection point is. We'll let the calculator handle that. going to ask us, if you're using an 84 calculator, ask you for 3 prompts. The first curve is y1, the second curve is y2, and since this thing intersects 3 times, we actually do want to put the cursor at the intersection point we're looked at, so it'll tell us, oh, look, 3. That's nice. So the first integral we need is the integral from 0 to 3 of the blue minus the red, if you want to think about it that way. We're also going to need another integral because these things change position. We're going to add to this the integral from 3 to, again, I don't know what the top bound is yet, but I do know that the integrals are going to change order. So big bracket in front. The first one is going to be the negative x squared plus 8x minus the second one, which is x to the third minus 8x squared plus 20x times dx, like that. So the next thing, let's go into the, again, we'll go into the calculator here, and we'll do the intersect feature. And again, we'll go first curve, second curve, and this time put the cursor on that guess right there. Oh, it is 4. I see maybe a little bit of optical illusion going on there. I guess I could have plugged 4 in manually to x into these equations to check it, but there you go. That's not too terrible. You could, in theory, do this without a calculator, but that would be absolutely bonkers. I'm having a hard time not swearing when I say how bonkers that is. So we're going to let the calculator handle all of the muscle for this problem. And we're going to do it because we already have these programmed into y1 and y2. We're even going to let the calculator handle all that stuff too. So let's go out here. We're going to open up F2, open up an integral. The first integral goes from 0 to 3. And I have this programmed in my calculator as y1 and y2. So that's exactly what I'm going to type in. I'm just going to go into alpha F4, I said, and do y1 minus y2 dx. That'll be the first integral, plus, let's bring up our another integral right there. This is the integral from 3 to 4. And we're going to change the order this time. Now it's y2 minus y1. Again, dx. And push enter, and it will tell us an answer that's actually, again, like I said, you could do this without a calculator, and it actually would be kind of a nice fraction. It's going to be 71 over 6, which is equal to 11.83 repeating. Yikes. Again, we said from the beginning we're going to let the calculator handle all of the heavy lifting on this problem, so, I mean, that is the answer to the question, so. That process is actually pretty straightforward when you get the hang of looking at the visuals of it all, too, there. We're only going to do one more problem today, and it's a bunch of derivatives. So let's get our pencils and paper out, and let's get cranking. Each one of these derivatives is going to require multiple operations, chain rule, product rule, all that stuff. So let's just get started. Don't let these intimidate you. These are much harder than anything you'll see on the AP test. But, again, if you train with these ones, you'll be just fine. Let's start with A, which is f of x equals 2x plus 1 squared times 3x minus 1 to the third. We're going to use this. You could expand all this out into a polynomial, but that would be a lot of work. We're just going to use the product rule, and the product rule is going to require the chain rule, but we'll deal with that in stride. F prime of x. Let's start with the original first, 2x plus 1 squared, times the derivative of the second, which I'm going to do in a big blocky parentheses right there. The derivative of the second function, we'll start with the outside part and do 3 times the inside chunk squared, just using the power rule with the third power there. We also need to multiply that by the derivative of the inside part, which in this case is 3. We will clean all that up in the next step. Plus the original second thing, 3x minus 1 to the third, times the derivative of the second thing, which is going to be very similar. I like to do this in a big old parentheses so I don't get confused. Again, using the power rule, we'll bring down the 2 and multiply it by 2x plus 1 to the first power now. And we have to multiply by the 2 inside because that's the chain rule there. And we can clean that up right now, actually. So leave all these blocky parentheses things alone, but you can multiply some numbers together. I see 3 and 3 here make 9, and 2 and 2 make 4. So we'll have 9 times 2x plus 1 squared times 3x minus 1 squared plus 4 times 3x minus 1 to the third times 2x plus 1 to the first. There you go. That would be the derivative of that first one. Question B is going to give us 1 over sine squared g of x equals 1 over the sine squared of x. Might be better to think about this as sine to the negative second power of x, like that. Because we are just going to use, this is a pretty simple chain rule problem, g prime of x. Let's start with the second power, or the negative second power. So that's the outside function. This will be negative 2 times sine to the negative third power of x. Again, just using the power rule there. Negative 2 comes down and multiplies, and then drops down a degree to negative 3. But because the inside function, which is the sine of x here, is a whole other thing, we have to multiply by its derivative, which is just the cosine of x. And honestly, that's the answer. You could leave it like that. You could clean it up a little bit. You could put negative 2 and the cosine on the top of the fraction and move sine to the third power of x onto the bottom, and that would be fine. That would be one way to do that. I mean, you could even, heck, if you wanted to divide a cosine by one of those sines and make it a cotangent, you could do that too. If you're bonkers. Let's look at question C. Question C has x times tangent of x squared, f of x. X times the tangent of x squared, like that. Again, all we're going to do here is just separate out the ideas. Don't panic. Again, the biggest thing here is psychology. It's like the answers are going to be ridiculous, so don't be afraid if you get a weird answer, because it's probably right. You're probably doing the right thing, and just don't panic. This is going to be another product rule, because at the end of the day, you have a thing, x, times another thing, tangent of x squared. So we're going to use the product rule with this. It's the original first, x, times the derivative of the second. And that's going to be kind of challenging. Derivative of tangent is the secant squared of the original inside. And since the inside is another function, x squared, we need to multiply by its derivative, which is 2x. That would be the chain rule there. So again, derivative of the outside is the secant squared. The derivative of the inside is the 2x. And now you can kind of clean it up in the next step if you want to. Plus, we need the original second thing, about the tangent of x squared, times the derivative of the first, which is just 1. So we'll just leave it there. So that's actually not too bad. You end up with 2x squared in the front, because these guys can combine together. It's all being multiplied. Times the secant squared of x squared, plus the tangent of x squared. And let's look at question D, which I have to write down here still. D is equal to cosine of x times the square root of x plus 1. Yikes. Is that h of x? No, it's still g of x. It is the cosine of x times the square root of x minus 1. Yikes, that's brutal. X plus 1. So again, we're going to use a chain rule for this problem, but then the inside is going to require the product rule. So there is a chain rule with a product rule inside of it, because this derivative right here will require the product rule, because it's two things multiplied together. It's x and the square root of x plus 1. But as far as the outside part goes, that's relatively easy. G prime of x, the derivative of cosine is just negative sine. Negative sine of the original inside. We're going to leave that alone right now. But now we need to multiply by the derivative of the inside, and that is not going to be fun. That's going to require the chain rule, or sorry, the product rule. So let's think about the product rule for a minute. The original first thing times the derivative of the second thing. And again, I'll draw a little thought bubble here, but we've seen the square root of x plus 1, or square root of, I guess, you could write the square root of anything. The square root of a, I guess. Its derivative, 1 over 2 roots of a. If you need help remembering why that works, it's technically a to the 1/2 power, whose derivative is 1/2 times a to the negative 1/2 power. Just a useful thing to memorize that right now. This will be 1 over 2 times the square root of x plus 1. And technically that's a chain rule, but the derivative of x plus 1 is just 1, so we don't need to worry about it. That's the first half of the product rule inside, so we'll add the second half, which is much easier. The original second thing, square root of x plus 1, times the derivative of the first, which is just 1. So it doesn't do anything. So we could do a lot of distributive property here, but I think we're just going to leave the answer in the simplest terms we can possibly write it as. G prime of x. It's going to be the negative sine of x roots of x plus 1 times x over 2 roots of x plus 1 plus the square root of x plus 1. Yikes, that's a kind of a bonkers derivative, but again, that's about as challenging as they get for us here. So, at least in Calc AB. Well, again, this video is longer. The videos are getting longer because I'm taking more time to explain everything rather than just running through the answers. So I hope they're helpful to you. I hope you have some time this weekend to get a little caught up. Maybe you're feeling a little more refreshed. This is the end of Chapter 5, so we'll be starting on Chapter 6 next week. We'll do a little bit of time on Monday and Tuesday for the review and the chapter test. And then on Wednesday, we'll start up with Chapter 6. And we'll keep pressing on. We'll keep going and do as much as we can before the AP test happens in May. So I'll see you in the next video. Don't forget, you guys are awesome. You can do this. You are amazing, and I'm really proud of you for making it this far. So keep it up, and I'll see you in the next video.